Hey everyone, it's me Engineer J, and in this video we have a new topic in highway engineering. So we have here reversed curve. So in our previous video we talked about a simple curve and compound curve, and we have this reversed curve which is different from the other two curves that I have previously mentioned. So basically in this video we will know what is reversed curve and how to compute the elements of a reverse curve. But before that, what is reversed curve? Now, reversed curve is a curve composed of two simple curves having a common tangent but lies on opposite side. Now, we have two different cases of reverse curve. We have a reverse curve for non-parallel tangent and reverse curve for parallel tangent. Okay? Now, reverse curve again, this is combination of two simple curve but opposite in curvature. So, we have this a simple curve concave downward and a simple curve concave upward. So, as what you can see, they have different in orientation. And for the element of curve, of course, we have PC here. This is the point of curvature. PRC, this is the point of reverse curvature. And PT, this is the point of tangency. Since we have two simple curves here, so we have different radius for each simple curve. So we have radius of the first simple curve and radius of the second simple curve. And since they have a point of intersection, so therefore they have a common tangent. Okay? Now, they have also their point of intersection or individual point of intersection. Now, for non-parallel tangents, as what you can see, the back tangent and the forward tangent has point of intersection. Okay, so from the word itself, it is non-parallel. But for the second case, if our back tangent and forward tangents are parallel to each other, just like this one here. So we have two cases here, so we will try to solve different example for each cases. So let's try to solve our example number 1. So in this video again, we will try to solve the element of the curve. But if you missed to watch or if you do not know what are these elements, so I have posted the link of my discussion on the derivation of simple curve elements. So why we need to compute these elements? So again, we need to compute or we need to determine the data or the value of the element of curve, because we will be using the values of this element to lay out our curves in the field. We have this first example here. We have two parallel tangents 10 meters apart are connected by a reversed curve. The chord length from PC to the PT equals 120 meters. So compute the length of the tangent with common directions. The second question is determine the equal radius of the reversed curve. And letter C is compute the stationing at the PRC if the stationing of A at the beginning of the tangent with common direction is 3 plus 4, 20. So this is an example of a reverse curve with parallel, backward, and forward tangent. So basically, this would be our figure. So this would be our simple curve 1. This is our backward tangent. And this one is our PC. And this point of intersection here, this one is our point of reverse curvature. And this one is our point of tangency. So individually, they have a point of intersection. Let's say that's our PI1, or you can say that's vertex 1. And this one is point of intersection 2. And from our problem, now we know that the radius here or the radius of two curves are equal. So let's say it's our R1, and this one is R2 as well. Okay, so according to the problem, we have two parallel tangents 10 meters apart are connected by a reverse curve. So therefore, according to the problem, these backward tangent and forward tangents are 10 meters apart. So therefore, their vertical distance is 10 meters. So we have this one. So the distance here is 10 meters. And we also have another given here that the chord length from PC to the PT is equal to 120 meters. So we have a chord length. So therefore, we have a chord length connecting PC and PT, which is equal to 120 meters. Okay? So therefore, it's 120 meters. So our first question is compute the length of the tangent with common direction. So we will be computing for the length of our tangent 1 and tangent 2 here. Okay, so how are we going to do that? Now we know that we have the distance between the two tangents, which is 10 meters, so we can actually put it here. So we have this length, okay, which is 10 meters. And we can create a right triangle, which is this triangle here. So we would have this triangle, which is, this length is 10 meters, and the chord length from PC to PT, which is 120 meters. So we would compute the value of our angle here. Okay. Now, since we know that this one is the angle of intersection 2, so therefore, the angle here is I2 over 2, correct? So we have I2 over 2 on this area here. So by using sine, we have sine of I2 over 2 is equal to the opposite, 10 meters, over the hypotenuse, 120 meters. So we would get the value of our I2 over 2, which is equal 4.78 degrees. So therefore, our angle of intersection of a simple curve 2 here is equal to 9.56 degrees. That's too small for a simple curve. But anyways, let's continue our computation. So we have I2 here, which is 9.56 degrees. If we have 9.56 degree as our angle here, that means we have also 9.56 degree as our angle on the point of intersection. So we have here 9.56 degrees. So since our goal here is to compute the length of the common tangent, now we know that the vertical height from this point PI down to the extension of our forward tangent is 10 meters, correct? So that means we can create another right triangle here, which is this one, in which the angle here is 9.56 degrees, and then this vertical height here is 10 meters, and we do not know yet the length of the tangent connecting PI1 and PI2. Again, this is PI1 and this one is PI2. So our goal here is to compute for the value of x. So that would be our question letter A. So basically, we can use here a sine. We have a sine of 9.56 degrees is equal to the opposite. We have 10 meters, and the adjacent we have x. So we have the value of x that is equal to 60.212 meters. Okay, so this is our answer letter A, which asks for the length of the tangent with common direction, and that is the distance from PI1 to PI2, okay, or the vertex 1 to vertex 2. Now for our second question, we are asked to compute for the radius of the two curves. So we, using the given condition that the radii of the reverse curve are equal, that means the two simple curves are similar. So all the elements of a simple curve 1 is equal to the elements of our simple curve 2. So basically, our tangent of the first curve is equal to the tangent of the second curve. Since we have a total tangent line of 60.212, so to compute for the tangent of the first curve, basically this is just 1/2 of 60.212. So that means our tangent 1 is equal to 30.106 meter, and that would be also the tangent length of our simple curve 2. Okay? So we will be using this data to compute for the radius of each curve. So question letter B are the radii of the simple curve. So we will be computing for R1 and R2, which again has the same value. So our tangent 2 here is equivalent to 30.106, as well as our tangent 1, our backward tangent, which is 30.106 meters as well. Okay? So we will just be using the formula that we derived from our previous video. So again, the link of the derivation of the simple curve formula has been posted in the description below. So we have the formula: tangent is equal to R tangent of I over 2. Okay? So therefore, if we evaluate this formula, so we have radius is equal to the tangent over tangent of I over 2. So since we have already the value of our tangent line, so we have 30.106 over tangent of 9.56 over 2. This would give us the value of the radius, 360.03 meters. So this is the value of R1 and R2. So that means this is our final answer for question letter B. Okay? Now for our third questions, we are asked to compute the stationing at the point of reverse curvature if the stationing of A at the beginning of the tangent with common direction is 3 plus 420. So we do not know yet where's the location of A, but we have this condition here that this is at the beginning of the tangent with common direction. So therefore, our A here is at this point, or at a PI1. Okay? So this is our A, which has a station of 3 plus 420. So we are asked to compute the station of PRC. But before we can compute for the station at PRC, we need to know first what is the station of PC, because we need to start our station from PC. Okay? So from PI2, or from point A, we have the station of 3 plus 420, and we have already computed the tangent distance, which is 30.106. So to compute for the station at PC, we just need to subtract the tangent length. So we have 3,420 minus 30.106. This would give us 30,389.894. That means the station of PC is 3 plus 389.894. Now, to know the station of PRC, we need to compute first the length of the curve of the first simple curve. So we need to compute first again the length of the curve by using the formula C is equal to Ri times pi over 180. Now in some book, instead of C, they use LC. So there would be interchanged in symbol for chord and length of curve. Okay, so you need to be careful with that, but it's up to you on which symbols or which designation you want to use. So we have C is equal to R. We have already computed the R, which is 360.03 times the angle of intersection. Since they are equal simple curves, our I here is 9.56 degrees as well. Okay, so we have 9.56. Then we convert this one into radian by multiplying pi over 180 degrees. So we have the curve length equals to 60.072. So to compute for stationing of PRC, we just need to add the station at PC plus the curve length. Now we have already computed the station of PC, which is 3 plus 389.894, but we need to express that in two numbers. So we have 3 into kilometers, so we have 3,389.894 plus 60.072. This would give us 3,449.966 meters, or the station at PRC is 3 plus 449.966. So this would be our final answer for question letter C. And now we have the second example here. Given the lines and direction as follows: AB is equal to 57.6 meters due east, BC is equal to 91.5 meters north 68 degrees east, CD is equal to 102.6 meters, and azimuth of 312 degrees. A reversed curve is to connect these three lines, thus forming the center line of a new road. Now, compute the length of the common radius of the reversed curve. So basically here, we need to draw the reverse curve first. Now, we have A to B, which is equal to 57.6, and that is due east. And that is our line AB, which is 57.6 meters due east. Now, BC is 91.5 meters, that is north 68 degrees east. So we have this line, which is BC and has a bearing of 68 degrees. So therefore, the angle here is 68 degrees and the length is 91.5 meters. And lastly, we have CD, which is 102.6 meters, and the azimuth is 312 degrees. And we know that azimuth of 312 degrees refers from south line or from the south direction, and thus we have to rotate clockwise from the south. So that means we have this line here, which is 102.6 meters, and the azimuth is 312 degrees, or the angle of rotation from the south is 312 degrees clockwise. Okay? And this is our C to D. So we draw now the line. So we now draw the curve. So we have this curve. So this would be our assumption, but according to the problem, the reverse curve has a equal radii. So therefore, the radius of our first simple curve is equal to the radius of our second simple curve. So never mind the drawing. So this is only an assumption. So our goal here is to compute the value of the common radius of the curve. So however, we do not know yet the value of the central angle I1 and the central angle I2. Okay, so our goal here first is to compute for the central angles or the angle of intersection. So how are we going to do that? Now we know that if we have I1 here, so we know that the value of the angle at point B is equal to I1. Okay, and the same as with the angle at point C is also the angle of intersection 2, or that is I2 here. Now we can compute I1 here by just looking at point B. Now we know that 68 degrees and I1 are complementary angles. So therefore, if we add this angle here, it should have a sum of 90 degrees. Okay? So therefore, we can say that I1 is equal to 90 minus 68 degrees. This would give us the value of I1, which is equal to 22 degrees. Now for I2, so this is now 22 degrees. Now for I2, we have this I2 here. Now we have this azimuth. Now to compute for I2, we just need to have this equation. Now we know that the angle from the south up to the line of up to the forward tangent is 312 degrees minus 180 degrees. So from the south to this point, so that is 180 degrees, correct? So minus 180 degrees, then minus this angle here, and we know that the angle here is equal to the angle at this point, since again they have the same reference line, and these two angles refers from the north. So therefore, this one is also 68 degrees. So we have minus 68 degrees, and the remaining angle would be this one, which is our I2. So therefore, our I2 is equal to 64 degrees. So therefore, the angle here is 64 degrees as well as the angle here. Okay? So again, our goal here is to compute for the common radius. But how are we going to do that? Now we know that if we have a tangent here, this is our tangent 2, and we also have tangent here, which is our tangent 1. So if we add the two tangents, so we have tangent 2 plus tangent 1, this would give us the length of B to C, which is 91.5 meters. So we have tangent 2 plus tangent 1 is equal to 91.5 meters. Now we know that the formula of tangent from the derivation of simple curve, we have R tangent of I over 2. So individually, we know that in tangent 2, we have R2, then tangent of I2 over 2. Now for tangent 1, that is R1 plus tangent of I1 over 2, and this equals to 91.5 meters. But we know R2 is equal to R1, so we designate this one as R. So we have R tangent of our I2 is 64 degrees over 2 plus R tangent of our I1 here is 22 degrees over 2, and this equals to 91.5 meters. So therefore, we can say then that tangent of 64 over 2 is equal to 0.625. So we have 0.625 R plus, now for tangent 22 over 2, this would give us 0.194 R, and this equals to 91.5 meters. So if you add the two variable, you would have 0.625 plus 0.194. This is equivalent to 0.819 R, and this is equal to 91.5 meter again. So to simplify it further, we have R, or the radius, which is equal to 111.722 meters. So this would be our final answer. So this is the value of the two radii. So 111.722 as well as the radius of our first simple curve. And that's how you are going to solve reverse curve with non-parallel tangent. And that's it for our discussion for reverse curves. If you have questions, you can comment it down. Thank you guys for listening, but please don't forget to like this video and subscribe to my channel. God bless and stay in good health. Thank you.